Our lead for this next talk is the lead of the engineering division here in Green Bank, Steve White. So some of these engineering questions that were just asked, you might want to pitch to him at the end.
Yeah, well, I'm hoping I'm going to cover that. So they almost asked the questions that I'm going to cover.
Perfect. Yeah, she goes. Take it away, Steve.
Yeah, so this talk is mainly on the receiver systems. It's from really all the way from the optics of the telescope to the, I'm going to end really at the fiber optic. There was another talk on back ends, I think, which will explain more about the digital signal processing, but it all works in conjunction to be able to do, state-of-the-art science. So I'll start out by talking about the GBT optics, and pretty much most of our feeds that are employed on the telescope for all receivers are corrugated two-mode feeds. I'll explain why that's the case, why we use those. We're up to 4 prime focus receivers and 11 Gregorian receivers for 8 slots. I'm sure you may want to know why we have so many receivers. Why can't we just have one? So hopefully that'll be answered by the end of this talk. And then finally, I'll go over about the new technologies that are make the observing mapping more efficient. And so there are really kind of 3 classes. There's focal plane arrays, then there's phased array feed receivers, and finally ultra wideband that we're developing. I'll go into a little bit of details and challenges of that. So that's kind of what I'll be covering. So let's start off with the GBT optics. So as Jay mentioned, it's an offset design. So how do you make the GBT? Well, first of all, you define a large paraboloid. You want to, you don't want the you want to offset design. So you want to design where the feed arm and focal point is not in the aperture. So how you do that? You define a large paraboloid to begin with. You define it by the focal point and the diameter you want, and then you specify a center of the dish, and then from that you sort of have to construct a cone with a half angle of 39 degrees, and that is sort of goes back to the feed design. So this image here is, you can think of it as how the prime focus illuminates the dish. And there was a question earlier about how the edges of the dish, and there's a property of these feed horns that I'll go over, and it's the taper. And so in order to maximize the aperture efficiency over the system temperature, there's a certain taper, meaning the feed illumination of the dish falls off at the edge, and there's an optimum value for that that we try to achieve. And so I'll go over that too a little bit later when I get into feed design. And so in order to make the GBT, you define a cone angle of 39 degrees. You rotate it 42.8 degrees, and you sort of chop out the metal from the parent paraboloid, and that gives you the primary reflector. So you want to be able to have a secondary focus, because that allows you, there's a couple considerations for that. That allows you lower noise temperatures, and at the lower wavelengths you can have smaller feeds, so you can illuminate a secondary focus, but you can't do that at long wavelengths. You have to use a primary focus. So we have a secondary optics that there's some considerations went there. It's mainly spillover. I'll talk about that, and the feed gain, which is 15 degrees. Notice it's 15 degrees versus 39. So it's almost a factor of 3. So that means you have your feed horn designs are about have a gain of about 3 times as much, meaning their aperture size has to be about 3 times the size of the prime focus feed. And so that goes in is one of the main considerations when you're doing feed design and the optics. So just so you know, we're all familiar with GPT now. So that as I've said before, the weight is 17 million pounds. The focal length of the parent probe is 60 meters. So the feed arm is 60 meters. There's one of the design considerations for optimizing aperture efficiency over system GSIST is, and we consider this in early days, is the location of the feed arm. If you notice that in Jay's talk, the more modern dishes have their feed arms on the bottom, and there's been some analysis, and that actually helps you lower or improve the aperture efficiency over the system temperature, because you get less spillover. The feed arm on the bottom, you're able to illuminate the dish, and some of your spillover from the beam sees the sky and not the ground. The problem with the GBT is that the prime focus is looking down towards the ground, so the spillover temperature is kind of high. So you really want to, and you'll see the system temperatures kind of follow that. You'll see that as you get higher, after you get past the receivers at the focal point, you'll see the system temperatures start to drop, and it's mainly just because the spillover temperature goes down, the part that spills over from the edge of the ditch. Surface accuracy, we use holography to measure that. It's that should have been micrometers. The micro got left off, but the track flatness, we measure that. It's there again, plus or minus 125 micrometers. Delta height of the track is 0.1 millimeters. And of course, it's a Gregorian secondary optics, meaning the subreflector is behind the focal point. So incoming waves strike the dish, go through the focal point, and then start expanding again, and then strike the subreflector, and then the secondary focal point is about right there. So there's a turret, receiver room and turret, and that's where all the secondary focuses are. You get to rotate the secondary focus with the different bands from L band up in frequency, whereas from below L band, you only have one focal point and one receiver. So that you have to change receivers in order to observe different frequencies below 1 gigahertz. So some of the considerations from in a little bit more detail. So if you think of the GPT in terms of aperture and aperture illumination, there's several terms that reduce your efficiency. Fortunately, the GPT was designed to have zero blockage, so that term is essentially 1 because there is no blockage. But there are other efficiencies are contribute to the total aperture efficiency, and one of them is illumination efficiency, and that goes into the optimization. So if you have illumination efficiency of 1, you're totally illuminate the dish to the very edge with no taper. But if you do that, you start picking up spillover, and then there's an optimization where the illumination efficiency times the spillover efficiency gives you an optimum aperture efficiency over the temperature. So that's where these two terms is where the optimization comes in for the feed design. And then there's a phase efficiency, and that just is a term that is you lose efficiency if your phase center of your feed is not at the focal point. And so feeds have phase centers that move around. And so there's kind of an optimum point for phase efficiency of signal frequency, but as you go through the bandwidth, you lose a little bit of phase efficiency. So we try to design the feeds to have flat phase response, but there is some loss there. And then cross polarization efficiency, that's kind of due to the feed design and the offset optics of the feed of the telescope introduces cross polarization. So it's the GBT, being an offset design, you sort of sacrifice a little bit for cross polarization. So it's not the greatest instrument for polarization measurements just because of that. We correct for it a little bit. There's a slight correction you can use to, and it's just the angle of the subreflector relative to the feed compensates a little bit for cross polarization, but only at the secondary focus, not the primary. So you lose a little bit there too. So this goes into a little bit. So so we try to the optimized TCS aperture efficiency. If you want to optimize aperture efficiency, what we want to do, the optimum is about 15 dB of taper, meaning the signal strength is about 15 dB, and it helps to understand these things by using a principle of reciprocity by thinking as a feed in terms of a transmitter. So in electromagnetic analysis, the feed acts the same as it was receiving the signal as it is transmitting. So we flip back and forth between those concepts to try to help you understand it. So a lot of these times I'm flipping back and forth, and it's really, we really receive only, but sometimes in the analysis and thinking about these things, you think of these as in the transmitting mode. So a lot of these slides look like we're transmitting from the feed, but we're really receiving, but it works just the same. And so there's an optimum, it's about 0.7, the optimum aperture efficiency, and that's with a 15 dB taper. And what that does is it reduces the spillover with the maximum illumination. So there's sort of a curve of taper versus maximum aperture efficiency over system temperature, and that maximum is around 15 degrees. So most of our feeds have about 15 degree of taper to maximize aperture efficiency over aperture temperature over aperture efficiency. But some of the feeds don't quite have that optimum because just due to the size, we had to make compromises, and we can't really get the 15 degree taper, but we kind of shoot for that as best we can. So one thing to remember, your beam shape is a Fourier transform or your aperture illumination. So when your feed illuminates the primary, the beam shape of the feed, the Fourier transform of that gives you the beam, the telescope beam. And so we try to, all these feeds are designed to have sort of a Gaussian shape as much as possible. So that what that does is reduce the side lobes and give you a more uniform beam without side lobes. But there again, we'll see in the some of the focal plane arrays where you have offset feeds, you sort of compromise a little bit with the offset feeds, and then and there's side lobes that start creeping in because the illumination is not uniform. The ultra wideband feed also has that issue. So basically, all these horns are designed as corrugated horns, and they're really two modes. There's analytical expressions for them. we can design them and build them and test them, and we know what we get like every time. And they're closed, nice closed form expressions. We can define the taper. There's a good impedance match with very little loss because of reflections. And for the GBT optics, all of our feeds are about 3 wavelengths apart. The aperture of the feed is about 3 wavelengths. So from 800 megahertz to all the way up to 3 millimeters, these feeds sort of scale with wavelength. They're pretty much the same design, but they just scale with wavelength. So when you're designing a feed, so there's a few parameters you can, the free parameters you can adjust. One is that, well, the aperture, of course, but it's tied to the GPT optics and that optimization of aperture, TCS over aperture efficiency, and you can change the flare angle to a slightly, sometimes, so this is a linear flare. This is sort of what the feed looks like. You mode convert here. So basically you have circular waveguide input. You have a low order mode, essentially TE11 mode, but you have to have a mode converter as part of the feed because you need 2 modes. You need TE11 and TEM01 to combine to give you a nice field pattern on the aperture. And so those feeds are very good at having, and by having uniform field lines on the aperture is how you get a nice far field pattern that illuminates the dish. Unfortunately, these are good to only about 2-to-1 bandwidth, and so that's one of the reasons that we have so many receivers, is because after you get exceed about 2-to-1 bandwidth, then you start introducing cross polarizations and distortion, and so they're not really optimized outside that range. So that's one of the driving reasons that we have as many receivers as we do. It's just the feeds are limited to about 2-to-1 bandwidth, and to get the best efficient mapping efficiency from the GBT. So this is kind of some of the prompt focus feeds. You'll see the corrugated feeds start at about 800 megahertz, and the reason that is because they just get too big. There's sort of limitations on the Stirling mount here and how much weight and moment the mount will take, and so you have to go to something different below 800 megahertz, and so we have like these cross dipole short backfire reflectors from 800 megahertz down. And you'll see from the next slide, you don't have quite as good beam shape, and you don't have the optimum taper, and so your system temperature sort of suffers from because of that. But that was one of the compromises early on. It's hard to make a corrugated feed that size at prime focus. So some of the other feeds are, as you see, they're all about the same. This KFTA feed, actually, you'll notice it doesn't have a linear taper. It's actually a profile design, and that was sort of a compromise. They're not quite as efficient as a linear taper feed, but we made a focal plane array out of them. So we wanted to be able to have a smaller footprint to be able to pack the feeds closer together. But most all of the other feeds are linear horns. You can see we go all the way down to W band, and then on the turret, you see L band and S band there. There's KU band. So basically all these feeds for the Gregorian receivers are all the same. They're just scaled. Okay, so we got the feed design. We know how to optimize it. We know what kind of taper we want. That reduces spillover. That gives us the optimum illumination. Now we go to why we have to cryogenically cool things. So basically, we operate in the realm of Raleigh Jeans, black body radiation. So we can describe all this analysis. We can describe with just a simple linear equation, KTB, and so with Boltzmann's constants and temperature and bandwidth. And that's pretty much when we're calculating system temperatures, we're using this equation for all the components. So so basically, when we talk about why we want low noise components is because every component adds noise, and in order to it's all about mapping speed. It's all about that aperture efficiency, the TSIS over the aperture efficiency. So you want the system temperature to be as low as possible, meaning you want the amplifier to be the lowest possible. And so in order to get that, you have to cryogenically cool the amplifier. So all these amplifiers are cryogenically cooled basically for to lower this TE is the equivalent noise input temperature, as if you're referring the noise of the amplifier back to the input of the amplifier. You want to reduce that and make that as low as possible. And that's the reason we cool these amplifiers, because there's a kind of a direct relation between the noise temperature added by the amplifiers and their physical temperature. So every one of our amplifiers are cryogenically cooled to about 15 Kelvin. They're inside cryogenic doors, and we have cryogenic systems on the GBT to keep them cold. After you get in the system scheme of things, after you get past the low noise amplifier, there's enough gain so your signal level gets high enough so the added noise from components after the low noise amplifier are really small, less than 1%. So we really don't have to worry about the components after the low noise amplifier. It really is the signal noise ratio is high enough, and the added noise, the equivalent temperature as of the components downstream is really divided by the gain of the amplifier if you refer it back to the input. So as long as the gain of the amplifier is high enough, which is about a factor of 1,000, about 30 to 35 dB, you don't have to worry about noise contributions from any of the system after the low noise amplifier. So quickly after you multiply the amplitude of the signal after you go after the low noise amplifier, you can come into the room temperature components, and that is shared among the different receivers. We have common IF, but you have to have each amplifier and each band cold and as low with a low noise temperature that fits the bandwidth of your feed to optimize performance. And so not in the ideal world, we'd have no losses in front of the amplifier, but the fact is there's many components in front of the amplifier. Since you cool these receivers, you have to have a doer that's closed, that's evacuated, so you can cool it down to cryogenic temperature. But that means you have to have a waveguide window. You've got to have let signals through that don't absorb the signal, but is strong enough to withstand atmospheric pressure. And that's kind of another area of research here we do. We're all talking about different components for waveguide windows. So, so the waveguide windows are typically a little bit of loss. If you don't cool your feed, sometimes feeds are too large to cool. they give you a little noise or give you a loss. Sometimes you have components so that you can observe both components, both polarizations. So you have to have a component before the amplifiers that allow you to observe both polarizations, and each polarization has their own gain IF channel. And sometimes you want to do circular polarization. You want your receivers to be in native circular mode, so there's a polarizer. So all these components before the amplifier raise your system temperature, and so you want to have those cooled too. So those components are also inside of the and cold, and they basically their contribution is just a function of their loss and their physical temperature. And it's much the same when we calculate these to get a total system temperature. It's the same relation as the atmospheric contribution. So I mean, if you're in some of these higher frequencies observing the atmosphere has you have a tau value, which is absorption from the atmosphere, and then there's a physical temperature of the atmosphere, and then there's also the air mass. But if you replace if you want the effective temperature of the atmosphere, you replace the equivalent. You want to find out the equivalent atmospheric contribution as far as noise, thermal noise. You in this diagram, you replace TE with TA, the physical temperature with the actual measured atmospheric temperature, and the loss with tau. Should be tau T times the atmosphere. That would be the effective loss of the atmosphere. So when we're making these system temperature contributions, the atmospheric contribution is very similar to loss in front of the doer. So they all look the same. They just effectively raise your system temperature contribution. So we want to try to minimize that. We want to try to minimize the loss. So these receivers, in order to have, if of course, you want to have maximum mapping speed. That's what single dish is all about, is maximizing mapping speed. You want both polarizations. You have to detect them separately. And so you have to have a device to do that. Most of these receivers have some kind of electromagnetic device that detects both polarizations. Most of the higher frequency ones, what's called open mode transducer, in which you can see sort of a square input. They take there's a transition from the feed to the OMT, and then you can see there's sort of two waveguides on the output that are orthogonal. And so it gives you, it separates the polarizations into two electric fields components, and then those get detected and amplified, and it's really a measure of signal strength, and those two ports give you a measure of polarization. So it's really if you want to do polarimetry, you have to do some mathematics on the strength of those signals in each one of those ports. Some of the lower frequencies have different time septum polarizers, and some of the receivers are native linear, and we have hybrids on the output that convert the linear to circular. So there's different methods depending on what band, what receiver, and what wavelength you're dealing with. Some of these receivers, like the KFPA, for instance, is native circular. So in order to make it native circular, you have to put a phase shifter in front of the OMT. So in addition to the OMT that separates the two polarizations, without the phase shifter, you have two linears. But if you put a circular phase shifter in there, then the output ports will be a measure of the left and right circular polarization. So if you have an experiment and you want to measure have an idea what the circular polarization is, you have to insert a phase shifter in front of the O2. It's like a quarter wave light optics, same concept. And but you in this type of receiver that has the waveguide phase shifter in as part of the receiver, you can't change it. It's fixed to be circular polarized. Some of the lower frequency receivers, there's a switch in there. You can switch in a hybrid. I think C band down. In that case, S band, I think, has C band down. There's an external switch that allows you to convert linear to circular. Everything above that has this OMT. Some of them don't have a phase shifter or linear polarized. Some of them do. So these are all heterodyne receivers. Most of all of them. We have some total power detections, but all of the block diagram looks the same. There's a feed, there's an OMT, a polarizer, an LNA, and then you after you come out of the doer, and most of these have an IF section like with a mixer and an IF amplifier and a bandwidth that sets the bandwidth as part of the receiver. But after that, this IF output goes into our common fiber optic links, which there are 8 of them. And then there's a matrix of switches up on the GPT in the receiver room that allows you to select the receiver and the particular IF you want and route it through the optical system down to the converter modules. There's another mix down in the converter modules that mix down to the sampling frequency of the digital signal processing. So the chain of the receivers kind of are all common after this block, and bandwidth is converted down to a lower frequency, and then at the sampling frequency, baseband sampling frequency, or bandpass sampling frequency of the Vegas, and all digital signal processing magic happens there. And then there'll be talks after this one on those back ends. Okay, so some radio source properties and sort of what kind of science can be done with these. We have 2 total power, which are photon counters. There's not, with the heterodyne receivers, you get phase and amplitude information that you can correlate and build spectrum from. 2 of these receivers are just total power. They throw away the phase information, and they're like photon counters. One of them is a Ka band receiver. It's got a built-in correlator on it, but it also is spectral. It has a spectral line mode, so it's not just a continuum receiver, but both. But you have to swap. You have access to both when it's on the telescope. We have a Mustang volumeter receiver. It's not heterodyne. It's just it uses transition edge sensors, and it just absorbs photons at 3 millimeters, and it's just a photon counter. It's self-contained. All of the total power information from these 223 detectors is just fed back over Ethernet link. And the rest, all the rest of these signal receivers are heterodyne receivers, where you get the spectrum bandwidth transmitted over the optics, and where our back-end processors provide you the spectrum, calibrated spectrum. So there's things of course you do H1, you do astrochemistry. Pulsars are a kind of different mode. They use frequency spectrum versus time, but it's still the same back end. They just change modes for it. But all the receivers are heterodyne to pulsars. Like I said, we've sort of suite of receivers is up to 14 now. I went over the polarization characteristics, and then there's we also do very long baseline array with the GBT. It's part of the network of receivers that does the phase calibration. We have a back end for the VLBI, and as part of the back end, there's a phase calibration, and everything is all the signals are referenced to a hydrogen major. So there's enough stability in the links and to the back end to do VLBI as part of the VLBI network. So this is sort of the system temperature of typical weather conditions. You can see down at the low end, there's a little bit of galactic contribution here, but pretty much pretty low until you get, this is around the little bump around the water line, and they go up till you get to the oxygen line where we can't see through. And then as you get away from the oxygen line a little bit higher, the system temperature is around 100K or something like that. It's mainly due to the receiver temperature is actually fairly low. The spillover is low, but the atmospheric contributions are mainly the largest source at frequencies above 40 gigahertz. So this is kind of so our prime focus receivers. You can see, as I stated earlier, the system temperatures are fairly high due to some galactic content, but mainly from the spillover. Those cross dipole feeds, you really don't get the illumination characteristics as you do with the corrugated feeds, and you can sort of see the big difference once you go to that 800 megahertz corrugated feed. The system temperatures really drop. The efficiency are pretty comparable from all the feeds. There's not much difference there. They're kind of the optimized value of the taper. As you can see, efficiency goes up a little bit because we're at the Gregorian now, and we have better illumination properties because we're illuminating the solar reflector. And the spillover is on the sky, so we can kind of over illuminate a little bit to get higher efficiencies. And these are sort of, you see the system temperatures are fairly low because the spillover is low until you start getting up to KU, and then when the atmospheric components are starting to have a pretty large effect. So this is just a photograph of some of our receivers. Ka band is a two. We usually have at least for these high frequency receivers at least two feeds, dual polarization. Ka band only has one polarization, but that was just because the OMTs introduced some gain instability, so the continuum was compromised. So we made that single polarization. The rest are dual polarization. As you can see, you get two beams with most of these. Q band, you get four beams, but they're sort of our slate of single dual pixel receivers. This is just a photograph. So the last photograph was you can see the feeds on top. Now we're in the receiver room where the common IF is, and you can sort of see how the L band protrudes really far down because it has a large OMT, and it's just at the very limit of what we could install at the turret. Okay, so now I'll transition a little bit about how to, we optimize, most of these receivers are about optimizing mapping speed or T-syst over aperture or aperture efficiency or system temperature, however you want to look at it, but it's really optimizing that number. And with a single feed, you're kind of stuck. You get, one feed gives you a certain aperture efficiency and a certain mapping speed, but in order to increase that, the solution is to add more feeds, more receivers in a doer. And so the focal plane array, the K band is one of our first multi-feed receivers. And as you can see, it's a 7-beam receiver. This is sort of the 2-foot turret hole. And as you notice, the efficiency is a little lower because we use the profile horn instead of linear horn. But you can see you can add feeds and receivers within the turret hole and not lose much efficiency. So there's a potential for adding many feed horns and receivers in one doer package to increase your mapping speed. It just scales with the number of feeds. But there's the downside is, and really the challenge is, it's hard mechanically to put that many feeds and cool it effectively. And so you would have, and so that's kind of the real challenge in making focal plane array receivers at K-band. Due to the aperture size, the beams on the sky are spread by the spacing of the feeds, and they're sort of 3 GBT beam widths away. And so you have to, when you're mapping, you have to sort of do some kind of pattern to fill in the gaps. Sort of, there was a question earlier about the plate scale. And so the plate scale for K-band is 0.17 half power beam widths per millimeter. That's just determined from the GPT optics. So we built this. That's as you can see, all the components I went over. You have to build. The takeaway here is when you build receivers and focal plane arrays, you have to build them sort of under the shadow of the feed, so you can get everything compact. So that was a real challenge with this receiver. We were able to do it. It was like I said, it was a challenge. This is the 7 beams all packed together. It's a pretty large doer. It's really about at the limit of what we can do mechanically. It would be very difficult. We could do it, but it'd be very challenging to put more feeds, receivers into one doer just because of cryogenic consideration. It's just hard to cool that much metal in that size. But one thing you do is you get increased mapping speed, a factor of 7. So the K-band focal plane array is really instrumental in mapping these star forming regions using pneumonia. And that's pretty much the reason that was the driving force to building the 7-feed array, just because K-band turns out to be one of the most oversubscribed regions in our spectrum just because of that water line. And so there's a lot of science and Milky Way mapping to be done, but there's just limited time. So increasing that mapping speed sort of increased our efficiency of doing that kind of science. There's one more focal plane array we have. It was built by a collaboration from Stanford, Caltech, BYU, University of Miami, and University of Maryland. And it's back in the lab. When you do your tour tomorrow, we actually have it down from telescope, so you'll be able to get a closer look at it. But it's a 16 array, single pixel or single polarization, and it was really a prototype as a way to. They try to make it scalable. So the idea is we start with 16, and we can go up to 144. Which, as you see, the feeds are much smaller, cryogenic packages are much smaller, and so it's much more feasible to expand this one to larger, to possibly 144 channels, just because of the size. So this is sort of the difference I'll point out is due to the bandwidth, you have to inject the LO within the bandwidth. And so that requires an IQ sampling scheme. So you have to, in order to get the upper and lower side bands from this receiver, you have to take I and Q channels and combine them to select the upper and lower sideband. Whether our other receivers, we just lock down convert, and we don't have to worry about that. But this one, due to the bandwidth, it had to include the mixer along with the low noise amplifier in the module, because the LO was injected within inside the band. The rest of our receivers, we either upside inject or low side inject below the observable bandwidth. And that makes it sort of easier to down convert and not worry about image rejection problems. But you can't do this with this receiver. So that's kind of one of the differences, one of the challenges they had to solve. This is some of the results from HCO using the 16 pixel. You can see the sort of the footprint and the increased mapping speed at 3 millimeters. And then this is the bolimeter, the Mustang bolimeter, which is totally it's primarily for the Zoldyck effect, for measuring scatter, Compton scatter and photons out of the cosmic microwave background, and just producing science results. Currently, it's been on the GBT about 5 years or longer, and so if you want to look up some of its results, and there's some papers being published now. Okay, so the final topic is really the phase array feed. So with technology advancements now, you can phase up the response from the feed horns to create a larger beam. And with a focal plane array, you're sort of stuck with a feed pattern and taper. With a focal plane array, on phase array feed, you can actually phase up all the different elements and optimize the aperture efficiency over T6. And by doing that, you can get better performance in the focal plane array, and you don't have that. You have a full sampled aperture, so you're mapping, so you don't have to worry about mapping different schemes for mapping to fill in the hole. You get one larger beam scaled by the number of beams you're able to form. And so that's kind of the next wave of technology that we will, that's occurring now. I think it's the sweet spot is for K-band phase array feed. We had a demonstrator, we built one here at L-band. It requires a lot of digital signal processing and understanding the baseline and calibration. It's kind of one of the drawbacks now, is it was kind of difficult to use, it's difficult to calibrate. And it was about a factor of 7 better than the L-band feed for mapping speed, but it's just so complicated to use that really we need more beams than the 7 to make it a viable instrument. And so with that said, I mean, this is kind of our results. We get, you'll notice we get about 25 Kelvin T-sis over aperture efficiency. And so that makes it a viable instrument. There's a group that was developing a similar camera at BYU as part of the group as Cornell, and they are building, currently have funding to build they're building a L-band phase array feed for Arecibo before it collapsed, but fortunately the optics were close enough for the GBT that they were shifted gears and are looking at building 69 element phase array feed for the prime focus of the GBT. I mean, they're putting the receiver together and testing it at Cornell, and back end is complete. And so they just need to get funding to make it a user instrument here at GBT. So they're trying to show the results and then apply for more funding. And finally, I'll go over quickly our ultra wideband receiver development. So with feed horns of corrugated feed horns, you're really limited to 2-to-1 bandwidth. With 6-to-1 bandwidth, with these ultra wideband feeds, so you get like 3 times as much bandwidth, but there's tricks you have to do and compromises you have to make. You have to add in these higher order modes in the proper way to get a good beam shape and high efficiency. So that's the real challenge. So currently we're on that route. We have one that's in development that looks like this. We started out in 2017 exploring all the options. You have to design these with a 3D modeling program. And then finally, we got far enough along that we built one. And part of the problem issue was building a waveguide window. We developed a quartz window for that, which is kind of really large. Did models on it, figured out how to did destructive tests to make sure it would stand pressure, and then finally, this receiver is kind of out in our outdoor test room, but you can see sort of the waveguide window. This is a special design quartz window, and that was one of the challenges of this receiver. It's sort of in the throat here. This is without the waveguide window, but we sort of had to compromise and insert the window down into the throat, which complicated the design of the thing a good bit. So here's some of the photographs of the development. And finally, we put it on the GBT and has some commissioning runs. And the takeaway here is that our model predictions are pretty close to what our measurements are. There's about a 6 or 8 degree Kelvin that we don't know what's coming from, but we got to find out. But with those measurements, we're able to have confidence in our model. And the problem with this one is there's some of the modal content of the higher order modal content was too much. And there's a little bit higher system temperature measured of the receiver temperature than we would like. We'd like to get it closer to this gray line. So we still have work to do to try to lower the receiver temperature. But ultimately, we think we can have a new design that we're working on now, and hopefully we'll be able to figure out where that excess noise temperature is and get our specs more close to what will make pulsar stronger. So that's kind of a wrap of all the receiver design. One thing I want to mention, every aspect of the GBT that I've talked about now, the optics, the EM components, the feed, was all designed by Sivasaran Srikanth. He passed away back in just last month. And if you really want to deep dive into the things I've talked about, all these GBT memos go into a lot of detail. I'm sure there's many papers on his feed designs, OMT designs, and NGDLA antenna analysis too. So if you want to look it up and have more, you need more information, and you really want to deep dive into these things, look up him. That's all. Thank you.
Looks like we have a question over here first.
So you mentioned after the LNA, which is hygienically cooled, your lead, it feeds into room temperature components. So is there some sort of temperature gradient between the two, or is it just literally?
Yeah, right. That's a good question. So that's one of the challenges of cryogenic receiver design, is to transition from that 15 Kelvin to room temperature. And so most of these receivers have, all these receivers have really 2 stages. So we have a 15 Kelvin and a 50 Kelvin. And so what we do is we sort of come out with waveguide on higher frequency receivers, for example, and we tie the output waveguide at 50K. And so the 15K sort of sees, and we use stainless steel with a low temperature, high thermic conductivity. And so that we do it sort of in stages to get out. And we do the same thing really with low frequency receivers and coax. We do the same thing. So we try to put a long bit of coax there that gives us high thermal resistance, and then use different stages of the refrigerators to lower the load on the first stage. And that's how kind of how we do it. Yes, sir.
Is linear polarization your default configuration?
Yeah, so all the feeds are native linear. And so if in order, so it comes down to, so the K-band, I don't know quite why they wanted circular polarization. It turns out if you cross correlate circular, you can measure linear. So for that reason, they were doing some measurements, and to get linear polarization is to cross correlate circular. So the decision was to make K-band circular polarization, and then that's where we put the phase shifter in there. The lower frequency receivers, they have the option you can do both, but they're kind of manufactured. You put a hybrid after the doer to give both polarization. You can just switch in and out and do either.
Oh, is RFI ever a consideration for deciding to select linear or circular?
Not really. RFI is a problem no matter what. So some of this, for instance, the S-band receiver has a cryogenic Knox function for XM satellite. So if it's really bad, so how we deal with RFI? Fortunately, in the Iridia quiet zone, the RFI is low enough that it doesn't saturate the first amplifier, and so we have that going for us. And so after we saturate, after we get by the first amplifier, the signals are low. But as you increase in gain, as you go down the system, the RFI gets multiplied higher and higher. So we typically put some kind of notch filter downstream if it's really bad, like the bedroom radar and elbow, there's a notch filter. And so that's how we deal it. But it's always an increasing problem. RFIs get worse. I'm trying to mitigate for it. Yes, ma'am.
When you talk about the gain that you have on the chain of the receptor, you said that you discard the gain of the after the first amplifier, right?
Yeah.
If you don't have cryogenics, so if you don't have your LNA cold deep down, can you discard also the gain of the other parts of the receiver, or you should take them into account?
So what was that last part of the question again?
So say you don't have cryogenics,
Yeah.
should you take into account in the temperature of the antenna the other parts of the receiver after the amplifier? Or
Yeah, right. Well, it all so normally when you analyze this, you refer all the noise to the input of the receiver, and that's what you do. And so when you do that, each stage after the first amplifier gets divided by the gain of the first amplifier. So when you refer it back, first amplifier. So your first amplifier generally sets the noise temperature of your system, and it doesn't matter if it's cooled or not.
okay.
It's just the first one generally sets it. But since the first amplifier sets the noise temperature, you want it as low as possible, and that's reason to cool it. So if you don't cool it, that just means your noise temperature is just going to be higher because your first amplifier has a higher noise temperature. And it's the same concept. Your other components really are affected as much.
And is there like some gain value of the first amplifier that you should take into account the rest of the parts?
Yeah. So it's usually we like to hit about 35 dB gain, which is a little over. It's about a factor of 2,000. So what that means is if your next amplifier after your first amplifier has a noise temperature of 2,000, then you divide it by the gain, which is 2,000, and so that's just 1 Kelvin referred to the input. So that's kind of what we're dealing with. It relaxes the amount of noise that your follow-up amplifiers have. So it makes it design a little bit easier. Nowadays, follow-up amplifiers are pretty low noise temperature. I mean, they're making room temperature amplifiers now below 100 Kelvin. And so their contribution, divide 100 Kelvin by 2000, and there's hardly any contribution from, the warm electronics.
There's a question online.
Why are the feed horns corrugated, and how does the angle and length affect horn properties?
Yeah, that's a good. So they're corrugated to. I'll just show it. Yeah, so they're corrugated. So to get these nice straight lines on the aperture, what you want with this HE11 mode, you have to phase up these two electric field components. And so the corrugations make the feed diameter look like a different diameter for the two modes. And that sort of slows one mode down in order to match the other mode up. And so the fields add up in the aperture to give you this nice, nice parallel field lines in the aperture. So you have to do that, and the corrugations allow that to happen. And the other thing is the length of the feed is primarily taper. The concept of tapering the feed pattern at the edge of the dish to some value, optimum value, is mostly controlled by the length of it, and that gives you the gain in the taper. So, so those two factors are what determines the illumination of the corrugated feed.
One more online.
So also, how are certain TE and TM modes isolated? Presumably all mode frequencies above a threshold would appear in the signal.
Yeah, so that's really the feed properties. They're really hybrid mode. And then if you think of the signal coming back the other way, you have hybrid mode here with these two modes. If going the opposite direction, this mode converter converts it back to TE11 mode, the lowest order mode of the waveguide. So, if you're thinking of a transmitting case, you really, the waveguide has the lowest order mode, and that kind of sets the bandwidth of the receiver. It's the lowest order mode of the waveguide, and then it propagates through, through the this part of the feed until you get to the mode converter, and then where these two are generated, and then they're phased up, and then the feed part of it is just the angle part, the flare angle is just what the feed pattern, far field pattern at the aperture is going to be, and so that's what you. So.
Any final questions for Steve?
You mentioned that there is an optimal value of aperture efficiency and around 70%.
Yeah. Mm-hmm.
Is that theoretical or is it for the green band?
Is that for what? For other telescopes?
It's just for the green band, or is it for all those?
Most all telescopes. Yeah. So I was going to mention that before. These concepts are complied to any telescopes, but mainly they're more important for single dish because this aperture efficiency and mapping speed really comes to play, and this low noise and high efficiency matters most. The same concepts can be applied to interferometers. Low noise is important, but not as much as single dish. So we go to extremes to try to optimize that, and every Kelvin counts here. And then that's the reason we're really careful about all this efficiency, low noise, and proper design. But the interferometers don't quite have, because they multiply their signals, they don't quite have the criteria that we do.
It's kind of a long question, so.
Okay, yeah, maybe we'll keep it for the break then. Do you have a short question?
Yeah, sure. How do I get access to the memos regarding the ultra wideband receiver?
Oh, you want the ultra wideband? There's not many on the ultra wideband.
So you listed a number of the.
Oh yeah, those they're online. They're on our website.
Okay.
They're available to the library, so, yeah. So yeah, I think you can probably Google or go to the NRA website and find the library page and have all those memos. But there's several there. There's ALMA memos, there's electronic division, journal reports, there's GPT memos, there's a full collection series.
Thank you for a great tribute to Sri and for a great talk.
Thank you.